Today, we are going to be talking about batch loading data and list columns. So this doesn't sound like a very functional programming topic because it's not functions and it's not looping. However, it is actually both, but mostly it'll be looping, which is what we've been focusing on through the first part of the term. What it is really is a more applied concrete example of functional programming practices. Okay, so last time we walked through that one example that I just showed you in the slides, basically. And this time we're going to start to walk through more of like real examples, actually working with data. Okay. So for our agenda, we are going to start by, oops, that was the wrong one. We are going to start by talking about the midterm, and there will be a quiz at the end of class. You will have 30 minutes for it. It's only 5 questions. I don't think that you're going to need 30 minutes, okay? But I'm giving you 30 minutes just in case. However, there is a time limit on it, and it is 30 minutes, okay? The reason is because this is supposed to be more of like closed book, okay? I'm not going to go around and look at your computers as you're working on it. If you're local, those of you on Zoom, I can't do that. So it wouldn't be fair for those in class if I did do that. So I'm just going to trust you and ask you to please not be using notes or the PowerPoint or whatever while you go through it, okay? The reason why it is a time limit is because it's supposed to be, if you know this stuff, right? Like if you know it off the top of your head, it should take you less than 10 minutes, okay? If you have to think about it more, then it might take you a little bit longer, and that's fine. But like it shouldn't, the time limit is there so that you can't really go and search for stuff easily, all right? I used to make it 20 minutes, which I still feel like is enough time, but I had quite a few people that ran up against the clock last time. I think it might have been because they were trying to look up stuff, but whatever. I just extended it an extra 10 minutes. Okay, so we will for sure have the last 30 minutes of class for that. Okay, the take-home midterm is technically assigned today. However, it has also been up since the start of class. Okay, so we'll go and actually look at that today, though, as a class, so that you can look through it with me and let me know if you have any questions or concerns on any of it. Okay. So we'll do that, and then we're going to review lab 2, and then we're going to get into the actual topics of today. We will mostly talk about map DFR, and we'll walk through some examples with that. I will then introduce list columns, and there's sort of 2 primary ways of working with list columns in the tidyverse. The first is with this pattern in the first sub-bullet here, group by nest, mutate, map, right? So you would group by nest, that creates your list columns, and then you create new columns by mutate map, okay? The second is nest by summarize, okay? Nest by is pretty new. When I taught this class last year, it was quite new. It had only actually landed on CRAN like, I don't know, a month before the course started. So it's a little over a year old in terms of being on CRAN, right? It's been out there longer than that on GitHub and everything. But I think this is generally a really nice way to do things. So I want you to be able to do it both ways so that you can kind of understand equivalent ways of doing the same thing. Okay. The top bullet here, this one is more general and will work all the time. This one will only really work with data frames, and actually this one will only work with data frames because you're doing group by nest, etc., mutate. But this, like the logic embedded in that map loop, is more general. Okay, and then we'll have the in-class midterm. Before we really get started, though, I also want to note, I don't know, like it's hard for me to figure out timing in these classes, like always, because sometimes we're going through things and we just kind of churn right through it, and I'm surprised at how much we get done. Other times we get to a specific topic and there's lots of questions and we don't get as far as I expect or whatever. So, so I'm not sure, but if I'm guessing, I would guess that we're not going to get through everything today. Okay, so I have it there just in case. And then what we end up getting through will kind of depend on how far we've gotten before the 30 minutes is up, right? And it will also depend on so what we do next week will depend on how far we get. So if we get all the way through, obviously we'll just start on next week's slides. If we get most of the way through, I may just say, okay, well, you can look at the rest of those slides on your own because it's important content, but it's not worth spending additional lecture time to eat into our next lecture. But if we don't get far enough, we're going to have to do that. Okay, so that's just sort of an FYI as we start here. Okay, all right, so let's start out by reviewing lab 2. Any questions before I get started on this though? Okay, good. Here we go. Let me get lab 2 open. Switch my share. And so move this out of here. From here, and then we'll go content post lab 2 index.rmd. Okay, so this lab had multiple parts, right? The first part was this multiple models part. So I asked you to start by just running this code. So we have a link, and then we're going to load that data through that line 25. And that gives us this data set called benchmarks, which looks like this. Okay, so we have the student ID, we have multiple cohorts of students, we have their special education status, their race, ethnicity, their free and reduced lunch status, their English language learner status, the season in which the assessment was administered, that's either fall, winter, or spring, and then their reading and math scores. So for each student, they have either 1, 2, or 3 assessments, okay, taken in the fall, winter, and or spring, okay? And this is all simulated, and that's what I went through there, okay? Then I asked you to run this code, which is just recoding wave to be numeric. So fall becomes 0, winter becomes 1, and true, which means everything else, becomes 3. Everything else in this case is spring. The reason I've written this case when like this is because if you don't have a default category, it can actually be problematic in terms of performance if you have larger data sets. So when you're writing case when statements with dplyr, you should always have your conditions, and then you should just leave the last one out and make that your default condition. And that will be better for performance than encoding every single condition, okay? In this case, it probably wouldn't make much difference because the data set isn't that big, but it can make a difference in other situations. Okay, then I'm asking you to fit a model of the form linear model, math, the outcome, predicted by wave, the thing we just created here through this recoding, right? For each student. So I'm fitting a separate model for every single student. If you have worked with multi-level models before, that is generally probably how you would do this. There's other ways too, of course, but that's one of the main ways that you would do this is if you were to do this in reality. But what's nice is actually this sort of an approach where you're fitting an individual model for each student can help you see things like the partial pooling and stuff. So there's reasons that you might want to do this, even if your ultimate goal is to fit one singular model for all students, okay? So that's the first part. And then the second part is to reproduce the plot that I have below, where you're basically just going to fill in these blank spots, okay? All right, so here we go. I'm starting out by setting my theme, and I have it set at 25, but for the purposes of the demonstration, I'm going to set it to 15, so it'll be a little bit smaller, okay? And then I start out, the very first thing I do is I'm going to split benchmarks, my benchmarks data set, by SID. So if I come back up here again, right, each SID is going to be its own data frame. So I'm going to have a list of data frames where each element of the list is a data frame for one student. Okay, So I can do that, and it's going to go on and on and on and on. And you can see the number of rows is going to depend on how many observations the student has, right? Between 1, 2, or 3. So every data set is going to have between 1 to 3 rows. Okay, there's 2, 1, 1, 2, 2, etc. Okay. Then I'm going, so now it's split. Now I'm going to loop through that thing. Okay, and notice I'm piping it here. We don't have to do it this way, but this is the way that I chose to do it. So I'm going to just pipe that list to map. So that list becomes the first argument here, right? This is where that is going. And then I'm using the tilde syntax, which is a shortcut for function.x, right? And then I have my model here, which I had up above, but I just say data is equal to .x. That means each element of this list is the new data set that you're going to fit. Okay, so I do that, and very quickly you can see we get a whole bunch of models. Okay, so each one has a model. But if we look through there, we can see the coefficient for wave is very often NA, and that is when the student only has one observation. Okay, and then finally we're going to map through this. So we're going to loop through all of these models now, and we're going to extract the coefficients. So I'm just passing the function coef. This is equivalent to if I did coef.x, right? That is the same thing. But in this case, because that's all it is, I'm just saying apply this function to each element. I don't actually have to do that. I can just give it the function that I want it to apply to each of them, and I get that. Okay, so now I have this coefs thing, which is a list for the coefficients, the intercept, and the slope for wave for each student. So every student has their own intercept, and every student has their own growth slope, basically, their wave, the amount that they're progressing across the seasons. Except, of course, those students that have one observation, they have NAs. Okay, so there's all my coefficients. Now, I'm going to loop through all of my coefficients, and I'm going to say loop through coefficients and give me just the first one, right? And that's going to be the intercepts. Okay, notice I'm using map double here. So that's going to return me an atomic vector of type double instead of a list. Okay, so I do that and I get all of my intercepts like that. Okay, then I do the same thing. I'm calling it slopes. You could call it wave or whatever. But I'm looping through coefs again, and I'm pulling the second one. Okay, which is the growth slope. Okay, and so there's all my slopes, and of course a bunch of them are NAs. Okay, finally, I'm going to put it together in what I'm calling IS, intercept slope. Okay, and so I say tibble, intercepts, and slopes. Okay, that looks like that. And then I say drop NA on the slopes. Okay, and then I'm saying row names to column ID. Okay, this ID here is not their SSID, right? Or their SID rather. So this is not the one that was in their data frame, but we need it anyway for follow-up work later. Okay, there's other ways we could do this. There's a lot of other ways we could do this. One thing we can do is anytime, so notice if I look at slopes again, notice I have all those actual IDs here. Okay, these are their SIDs because that's what we split it by. So there's a function, which I think I might even use later down here, but it's called nframe. Okay, nframe, if we did nframe on intercepts, what it does is it's going to create a column called name, which is all the names of those elements, and then values, which is all of the actual values from that. And that'll put it in a data frame. Okay, so and if we look at the help documentation for this nframe, you can see you can rename these things, right? Name and value. So I could say nframe intercepts, and then I could say, let me do it like this. And then I could say name is equal to SID. I'll put it in quotes. And then the value is equal to intercept, right? And that gives me a tibble back like that. And then what's cool is I could then, so I could call that my int, right? And then I could do the same thing with my slopes, that call it SLP for slope. Basically just copy this, but I'll put slopes, okay? And then I'll call this value slope, right? And then what I could do now is just do left join intercepts with slopes. And that, wait a minute, that's not what I want. I want int with SLP, right? And that will give me the actual SID. Okay, so if I wanted to keep the SID, that's one way I could do it. And then I could, you know, drop NA on slopes from there. Okay, so I'll call this IS2. Okay, oops. Oh, not on slopes. It would be on slope. All right, so IS2 now looks like this. Okay, so I'll keep that in there just as reference. But that's one, there's of course many ways we could do it, but that's one way we could do it. Okay, now we're going to create that plot. Okay, so I'm starting out by I'm just going to copy and paste that code that I had from up above, and then we need to add some things here. Okay, so we have geom AB line. AB line stands for intercept and slope. Okay, so you give it two values, one for the intercept and one for the slope, and it will then fit those things. Well, if I look at my IS, oops, hang on. If I look at my IS data frame here, right, I have this ID. It is not the SID. Again, to reiterate, this is not the SID. It's just a ID to identify each student. And we have the intercept and the slope for each of them. So what we can do is we can say the intercept is this intercepts column. The slope is this slopes column. And then the group is the ID. Okay, so that means, in other words, I want separate lines for every group. Every group is an ID, so I want separate lines for every person. Okay, and then I have I just specify the data as IS, and that gives us should give us a bunch of lines, but it's not appearing to. Maybe I have to specify more things first. Okay, then I just added geom smooth. Let's see if that adds it. There we go. So that's looking weird and not great at this point. And that's mostly because our axes are kind of messed up. Okay, and that was actually probably what was going on in the first step too. So what I'm going to do is scale X continuous. I'm going to set my breaks at, this is just more cleaned up, but notice how it goes 0, 0.51, 1.52. I'm going to set the limits at 0 to 2 and the breaks as 0, 1, 2, but I'm going to put the labels as fall, winter, spring. Okay, and this is still going to look weird, but at least that will clean up the x-axis. Right, fall, winter, spring. Okay, now scale Y continuous. This is where we're going to actually clean this up. And up above here, I have some additional code that I ran. So I said, what's the minimum of the intercept? It's 117. Okay, and if I'm thinking about the slope, what the maximum value is, I want to say, okay, what's the maximum of the intercept value, all of these, plus 3 times the slope value. Why 3? Because that's what the spring value is. Okay, so we're going to say the intercept plus, actually it should be 2 because it's 0, 1, 2. Oops, I don't know what that was. Oh shoot. Okay, well, it's running everything now. All right, so let's just run this again. 257. So the max value should be about 257. And now that I have the whole thing printed here, you can see that it is probably about 257 over here. Okay, so what I'm going to do down here on my scale Y continuous is I'm just going to pick some values somewhere in that range. I had 300 here, and that's, I think, what I maybe had up above. But instead, let's try going with 270. Okay, because I had miscalculated that. And there you go. Okay, Now we have every line for every student. And then we have this pink line, which is like the average across students. Okay. I also have down here some additional alternative code on how you could do this same thing. So we could do this instead of using the piping like I did above. We could do this in separate rows. So first I split the data frame, then I fit the models to each data frame using my split df object, right? And then I extract the coefs from them. Notice that this code on 139 is the same as this, right? So this tilde.x, we don't have to do that in this case. We can just say coef. And then pull the intercept. This is alternative notation to pull the intercept. And this is alternative notation to pull the wave slope. Okay. We could also on 144 do wave like that. Okay. Either way, all of them are good. It's just alternative ways to get to the same thing. Okay. Questions? Okay. All right. Part B. Now we're working with recursive. Okay, so we're basically this is data that came back from an API call, and they're big, nasty lists, and we're going to loop through them to pull out different things. Okay, so there's multiple lists in this package, all about Star Wars. And so we can start out with this SW Films one, and I'm asking you to identify how many characters were represented in each film. So let's start out there. So if I look at the structure of Star Wars, you can see it looks like this, okay? And it might be easier in this case to do this. Okay, so we see that there are 7 elements to the list, okay? This is called SW Films because each element of the list represents a different film, okay? So this is one film, this is a second film, this is a third, etc. Okay? And for each of these, you can look at them. Like for the fourth one, the title is Revenge of the Sith, okay? And we have the opening crawl and the characters and all of that stuff, okay? We can look at the third one, or the second one, and see that it is called Attack of the Clones. Okay, so again, we are going to use this list to identify how many characters were represented in each film. Okay, well, let's look back at this again. Let's look at the first one. And we see we have, let's see, title, episode, opening project, characters right there. Okay, and you can see right here that this is an atomic character vector of length 18. Okay, each of these is an API call to that character. Okay, so it doesn't actually tell you who the character is. It gives you the API call to go access more information on that character, because there's a ton more information besides just the person's name. Okay, or just the character's name, because I guess a lot of them aren't people. Okay, so what we're going to do then is we just need to loop through this bigger list, this list of length 7, and we need to find out how long this character's vector is for each of them. So we see for the first one, it's 18. For the second one, it is 40. Okay, so all we need to do is loop through it and see how long they are. Okay, so again, this is just more manual. One way that we could do this is by starting out with just the first one, right? And then I can pull the title by saying film 1 title. So that means if I want to pull all the titles, I could loop through SW Films and say, give me the title, just like I did for film 1 here, okay? So I called this film 1, and I just grabbed the first element of film 1, and then from that I can just use $title because they're named, and that gives me the title. So now I'm going to loop through SW Films and say, give me all the titles. But notice I'm using map_CHR, map character, right? Because I want a character vector in return. Okay, so I do that and I get all 7 titles. Okay, so there's the titles. And then to get the number of characters, I'm going to loop through SW Films and grab characters. Okay, so when I just do this, I'm going to get a list back with, again, all of those API calls for the different characters, okay? And so then I can loop through that and say map double, what is the length of each of those? And I get 18, 40, 34, 34, 26, okay? So that's how many characters are in them. If I wanted to, then I could also say, okay, now set the names of those things to the titles that I extracted up here. And we get an atomic vector in return that has named. So it's a named atomic vector where each element of it is the name. And then this is the n, okay? So we can put this together in a data frame like this, or similarly, using that n frame I just talked about, we could do it like that as well. Okay, any questions there? All right. The second part of this said use the SW species this time to identify how many species have known hair color and identify what those hair colors are. Okay, so we can look at the structure of SW species, or again, especially when I'm on a limited, I might be weird, but I actually prefer this output down here, but it's harder when I'm projecting because it's so zoomed in. So that's where the view on it becomes nice. Okay, so here's SW species. So there's a bunch of different species, right? And we can look at these, and here's the first one is called Hut. The second one is called Yoda's species, okay? And you can see down here we have hair colors, okay? And for let's go back to Hut. For hair colors, for Hut, it has NA, okay? And then for the second one, for Yoda's species, the hair colors is brown and white, okay? So that's what we're trying to extract, okay? So again, one of the ways I would probably do this is I would start by just grabbing the first species, which looks like this. This is all the elements of that list for the first species, right? And I can look at the names of species and I can see all of the different things that I can grab for first species. So I can grab first species hair color and I get NA, exactly what we expect. So now I know all I got to do to get all of them is loop through SW species. And just like we did before, we're going to go tilde dot x and then grab the hair colors. Okay. I'm using map CHR for map character to get me all of them. Okay. So finally, now to get what I actually want, I'm starting out with a tibble here. I'm going to say species. I'm going to map through species and give me the name. Then I'm going to say hair is equal to loop through the species and give me the hair color. Okay, so that's going to give me a full data frame that has everything. And then it's sort of vague. I said known. So to me, that means I would filter out any that say none, NA, or unknown. But you could say that none is known. They just don't have any hair, right? Hair colors or whatever. So that it's a little vague, but I'm not really worried about how you did that. But here's what I ended up with, and I would expect you to end up with something similar in some way, right? The species name and then the hair colors that they have. Questions on that? Okay. Finally, the last part where we were making some API calls. I'm guessing for most of you, this is your first time ever interacting with an API, and that's cool and that's great. It can be a little bit tricky, but it is, if you can get good and, well, I wouldn't say good. I would say if you can get confident in working with an API over the web, that's great news for you because a ton of data on the web is stored in these REST APIs, which is what we're working with here, okay? And so by sort of getting confidence that you can do this, it opens you up to being able to access a whole bunch of additional data, okay? So, you know, social media is a very common example, but there's also all sorts of natural resources data and all sorts of other stuff that you can get through web APIs. And each API is a little bit different. The way that you interact with them is always a little bit different. So that's why I said I amended very quickly that not getting good at working with APIs, but it's more getting confidence that you can, and then you can learn all the intricacies of each API that you end up working with, okay? And it's always going to look something like this process that we're doing here, okay? So this is just some background stuff. And then we go to the Pokemon one, all right? So there's a package called HTTR that we're going to use. It has this function get, okay? So to get the first ability, we say get, and we pass it this link saying, give me, and this is just to the API, right? And we went and looked at this before, but we can do it again real quick. So if we go here, oops. Maybe it's like this, okay. Here it is. Okay, so here it is, and this is what we were using, right? And then it gives you some documentation here, and you can see there's all sorts of stuff. Here's the API v2. So here's all the documentation. This is how you work with it, right? And so this is what we're doing here. This is we're saying, give me the abilities for the first Pokemon, okay? And so I do that, and I get back this thing that just looks like this. Here's this response. Here's the date, status, whatever. That's not very helpful to me, right? Because actually that's just printing out like a summary of what it did. Underneath, it's got a bunch of JSON data. But JSON data doesn't interact with R directly very well. And so what we're going to do is we're going to parse that JSON data into a list, okay? And so that's what this content parsed is going to do. And so then when we do that, now we have this ability one thing, which looks very similar to the list that we were working with Star Wars, but now it's Pokemon, okay? So the first thing I said is that this one is denoting that it would be the first ability in the database, okay? Because we're looking at abilities, okay? So I think I said that wrong just a second ago, but that's fine. So if I change that to a 3, for example, that would give me the data for the third ability. So I asked you then to use per to write an API call to obtain data on the first 5 abilities. And again, I sort of mentioned this here, but the only reason we're limiting it to 5 is just to limit the amount that you're downloading. Okay, but it could be 25, and the code would be no different, except I would change 5 to 25, right? So again, there's multiple ways to do this, but the way I chose to do it is by first creating all the links. So I just took this first part and then just pasted 1 to 5 on them. So we got abilities, and it looks like that, okay? Then I'm going to say map through abilities and apply the function get, okay? So this is equivalent to map abilities tilde get.x, right? Just like we did it before, but because this is the singular function that I want to apply to each ability, each element in the abilities vector, I can just pass it the function, okay? So I got that, and now I can look through that, and we get all of that same summary sort of looking thing that we got before, but for the first 5. And again, that's not super helpful. So what we're going to do is now loop through that again and apply the function content, and I'm passing it this additional argument parsed. Okay, so this is getting passed to this function, and this is equivalent to this code here. So map Poke's ability tilde content.x comma parsed. Okay, this should have a space, but that's those two are equivalent syntaxes. And there's not one that is necessarily better than the other. You should always preference readability over compactness. But I'm trying to show you different ways of writing the same code. Okay. So finally, now we have Pokes, which is going to be a list of length 5. Right. If I say what's the length of pokes, it's 5. Right, for each of those 5 abilities, and each of those has basically a list inside it, right? So I think they're probably all going to be 9. Yes, it looks so. Okay, and that's like different information on the specific ability. Okay, so that's how we get the actual abilities. And just as an FYI, there is actually a better way to do this if the goal were really just to work with the API, which is I think you can do something like this, where you go like 1-5 or something like that. It might be 1:5. I can't remember. You'd have to look at the documentation. But so you wouldn't actually have to write this loop if you were really working with this API, but you have the tools to do that anyway. So whether you write the loop or they write the loop, it doesn't really matter. And obviously looping is what we're practicing. So I had you do it instead of having them do it. Okay, so now we're going to use the parse data to create a data frame that has the given ability, so the name of the ability, and the number of Pokemon with that ability. Okay, so let's look at this. I'm starting out with just 3. Let's look at pokes again. Okay, so here's the 5. If I just look at this first one, you can see it has all of these things, right? And what I can see down here is, let's see, there's this name right here, which is stench. Okay, so that is the name of this ability. And then the Pokemon, that's going to be buried in there, but this is a link to one of the Pokemon that has that ability. Okay, and if I go here, this is the link to another Pokemon that has that one. It's called Grimer. Okay, and so what I need to do is once I get to this Pokemon one, I just want to know what's the length of Pokemon, because Pokemon is going to be, each of these represents an individual Pokemon, right? So for example, for this first one, which is Stench, there are 10 Pokemon. Which ones they are, I don't know at this point. I just know there are 10 of them. But I didn't ask you, for this part anyway, which Pokemon they were. I just said how many of them have that, right? So if I'm just looking at the third one, I can say pokes 3, right? That's going to give me all the data for the third ability. And then I can say $name. What's the name of that one? It's called Speed Boost. Okay. And so then I can say, okay, well, for 3, what's the length of Pokemon? And it's going to tell me 12. Okay, so that tells me there are 12 Pokemon that have Speed Boost. Notice again here, and this is, I have tried to emphasize this, but I maybe haven't emphasized it enough. I am trying to solve the problem for one singular case. Once I've figured out the logic for one singular case, then I can extrapolate that logic to loop it through and apply it to all of them. Okay, so I've figured out how to get the name. It's just a named element of the vector, name. So I can map character on the Pokies to get the name. So these are the 5 names of the abilities. Okay, and then I can map int to give me the length of Pokemon, and that's going to be all the lengths of them. So then I can put them together in a data frame like this, and it ends up looking like that. Okay, questions there? Yep.
When you work with JSON data, do you always do the parse thing to kind of get that?
So I hesitate to say always, because there are cases where you want to actually write to JSON. And so it might be that you're pulling in JSON and immediately writing it to some other program or something like that. But generally, if you're working with it in R, then yes, you're going to do content parsed. There are other packages out there too. There are 3 main ones that read and write JSON data in R. And so those can give it to you in slightly different formats. So for example, it might be that your workflow is best to grab the data and just immediately write it out in JSON as like your first step. And then a second step, read it in with one of those other JSON readers to get the data in, because it'll bring it in a little bit different format. And maybe that's better for what you're doing. Other questions? Okay. All right. The last part was this bonus. And I warned you beforehand that this is quite difficult. So if you got it, great. If you didn't, don't feel bad, because it is extra credit for a reason. It's hard, right? But the idea for this one was to create another data frame that lists the names of the Pokemon with this specific ability. Okay, so we have those 5 abilities. I want to know now not just how many of them there are, but what the names of those Pokemon are that have them. Okay, so I get my abilities like this, Okay. And then the second thing I'm doing just to make things easier for me is I'm going to loop through the pokes thing, which is all of them. It has all the data on everything. I'm grabbing just the Pokemon thing from there. Okay. So if I do that, you can see this is just for the first one, right? And it has, this is just for the first ability. And it lists all it, you know, before we were just calculating the length of this thing. It was 10, there's 10 Pokemon. But within each of these, we have like 2 layers deep. We have this, the name of this thing, which is Gloom. Okay. And the second one, we have Grimer. But notice how I'm having to click twice every time. So it's buried in there pretty good, Muck. Okay. So that's why it's so difficult. So there are many different ways that we can do this. Here is one, I'm going to show you a couple different ways, but there's far more ways than just what I'm going to show you, okay? But what we can do is P double bracket 1, that's going to give me all the data for the first ability. And then double bracket 1, that's going to give me all the data for the first Pokemon. Right, and we can see is hidden, Pokemon, Pokemon name, Pokemon URL, and then slot. And so then from there, we're just going to grab Pokemon name, and we get Gloom. Okay, so again, that's pretty buried in there. And notice we've already gone back a layer too from this by, like, this is, if we wanted to do this from pokes, we'd have to go double bracket 1, double bracket 1, double bracket 1. Okay, no, that doesn't work either. That's not gonna work. So yeah, so it's slightly different than that. I don't know. I have something a little bit wrong in my logic there. But anyway, once we figure this out, which again, very nested in there, then we can access all within one ability. Okay, so here's the first ability, and we can pull all of the names for that ability. And here's all of the names for the second ability. Okay. And so then there's a couple of different, there's a ton of different ways we could do this. But one way we could do this is we can do a nested loop. Okay. So we can loop within a loop. Okay. Generally, I've mentioned this a couple of times. I try to avoid nested loops. The logic becomes really difficult, but I'm going to show you how to do that first. And then we'll talk about how to do it with avoiding the nested loop. Okay, so here I have mapped. This is my outer loop. Okay, so I'm going to map through P, each element of P, and then within there I'm saying function PokeList. Okay, so there's going to be a list within there. Then I'm going to map character through PokeList, and this is, notice PokeList just becomes the new thing that I'm looping through on this. So I solved this for one of them, the looping part, and now this. Right, if I copy this down here, it looks exactly the same. The only thing is, instead of doing it for 1 and then 2 and then 3, right, I'm going to do it for all of them by saying function PokeList. Okay, again, this could be like X or whatever, but, and I could even use the tilde twice, but then I have 2 dot X's, which is really confusing. So in these cases, I think it's better to use function and try to use a name that makes sense. Okay. So I do that, and now I get all of my Pokemon in a list like this, okay? Or with the original, let's see. Yeah, so this is, in this case, I did use the tilde twice, but I'm using my original Pokies, right? I have map through Pokies, and then I'm going to map character, and I have .x, and then I have tilde, and then I have .x Pokemon name. Okay, this gives me the exact same thing. It's just working with the entire Pokies thing instead of just P. And this one, I would argue, is much less readable. Does the same thing. It's more compact. It's less readable in my mind, especially because we have this .x here and a .x there. And it can get confusing as to which .x is referring to which, right? So I think this is much better up here. Okay, but we can check them, and we see that they are indeed identical. Okay, so either way is exactly the same. Better, in my opinion, is to write a function, which is an extractor. Okay, so it's a function just to extract something. So I'm calling this function PokeList. That's the name of the argument. And then I'm saying map through PokeList and get .x Pokemon name, right? So this is exactly this, basically, right? And so I do that. And now I can basically loop through P and then just apply one function to P, which is this extract Pokemon name, okay? And so we can see that's the same too. So again, we could also do this like this, right? And so this is pretty clear what's going on now on this slot, on this line. We're extracting the Poke name from each element in P, okay? So that would be more my preference. And we can see again that Pokemon 2 and Pokemon 3 are identical because 1 and 2 are identical. That implies 1 and 3 are also identical, right? And lastly, we could also do it through more of a piping framework. So here I'm using pokes, right? My whole thing, I'm getting just Pokemon. Then I'm going to loop through that and apply extract Pokemon name. And then I'm just checking to see if this one is identical to Pokemon 3, and it is. Okay, so that's the way to do it. But in each of these, you can see I still end up with this list that doesn't actually tell me the ability for each of these, right? So what I want to do is get the ability, which I have up here somewhere, right here, right? These are the 5 abilities, and the list that I have is of length 5. So what I can do, and this is sort of a bit of an introduction into what we're doing today, is I can just say, give me a tibble with Pokemon and ability. Okay, ability is, Pokemon is a list, right? But the list is of length 5. Ability is of length 5. And so when I do that, we get something that looks like this. Okay, so this is a data frame where we have the ability here, and then we have the list here. Okay, so these are the 10 characters for this one. And what we can do then is unnest this list, and we end up with something like this. So here's all of the Pokemon and their corresponding ability. Okay, and then a little bit of an alternative output. We could do the same thing, but then I group by ability and summarize to collapse them. Okay, and that doesn't look very good like that, but if we were to write it out, you could see it looks more like this. So here's our ability, battle armor, and then we just have a list of all of the different Pokemon that have that ability, separated by comma. Except we have type null. That's probably wrong. Okay. Any questions on that? That part is hard. Like it's just hard. But hopefully some of you are able to get it. Yep. Yeah, here.
Yeah, that's the equivalent of like nesting loops, right? It's just like that you will find it somewhere else. So like what you don't recommend is writing out the nesting.
Yes, that's right. So basically it's the exact same thing, which I think is what you're saying. But it's taking the looping part out and making it its own function. So then when you're reading the outer loop, it's just like, oh, okay, I'm applying this function to each element of this thing, right? But then, and so like, that's where like your naming of things becomes very important, extract Poke name. So it's very clear, like you're looping through this list and you're extracting the name for each of them, right? Which is much more easy to read than, okay, I've got this loop. Okay, so I'm imagining going through each element of the loop. Okay, and then I got a loop inside of that. So now I got to think 2 levels deep. So I'm inside one, and then I'm doing another loop in there. What am I doing, right? And so this allows you to sort of break that apart so that you can focus on the outer loop very easily. Like to each of these things, I'm applying the name. And then if you want to know, okay, well, what are we doing when we're looking at the name? Then you can go to that function, which is going to more naturally allow you to focus on just one individual thing again and loop through that rather than trying to think of both levels of nesting at the same time. Does that make sense? So it can make your code much, much, much easier to read. And that's the goal. It's not about efficiency. but it can make your code much easier to read and much easier for you to understand, which leads to fewer bugs and all sorts of other goodness. Basically, the goal is always to write your code in as simple a way as possible. Almost always, if I would, and I think most people, just about everybody I know, I don't know anybody who would argue this really, would say it's worth sacrificing even some efficiency if it gains you clarity in code. Because if you just think about it from an organizational perspective, right? Like let's say you're the CEO of a company, you have a bunch of employees that are writing code all the time. What's the most expensive thing you have? It's your people, right? And so if your people are spending a bunch of time trying to figure out what's going on in this code, that's going to be way more expensive for you than just using a little bit more compute resources. Okay. And yeah, so compute time is cheap, people are not. So you should, with few exceptions, always preference more readable code than more efficient code. Okay. So I guess it depends on what your goal is. Generally, like you can combine lists just like you can combine vectors. So you can use C on two lists and it'll just put them together if that's what you want to do. But if you want to like merge data frames within lists or something like that, then that's going to be more difficult. So I guess, can you clarify more what you mean?
Yeah, like I had a list that had like the 5 abilities.
Uh-huh.
Another list that had like all of the Pokemon.
Uh-huh.
That came up within those like.
Oh, yes. Okay.
So I had these two kind of like different types of lists.
Yes, I see what you're saying. Yes, so that is going to be more difficult. And basically so let me just repeat so that it's captured on the recording. So like you're looping through all the abilities and you get the names, for example. So now you have the 5 names of the abilities, but then you loop through again to get all the Pokemon associated with it. And that's a very different length from the 5 because it's every Pokemon that has it, right? And so that's where like you basically it's a much tougher problem. So you want to combine them so you can say here's the ability that has these Pokemon, but you can't really at that point. If you have made your list so that it's sort of flattened and it's just here's all the Pokemon, then you've kind of lost that higher level of structure that sort of ties them to the ability. So that's where you have to be really careful about whether you're using map or map character or whatever, because you have to make sure that you're maintaining that structure. So like when I was doing it right, it was a bunch of different Pokemon, but the overall list was still of length 5, which was and so that's just, yeah, I don't have great advice on that other than it's something to look out for. And if you know that's a goal, like at the end that you want to combine them, then they have to be the same size or you're kind of out of luck. Unless like it's possible that you could have names that identify them or IDs or something. So you could have one list that has like, is of length 200 and another one that's of length 5, but they all have names that are associated with the same 5 elements of the names over here. Then you might be able to you could combine them. It's still not going to be as straightforward as like a merge, but generally the best way to do it is try to do your looping in a way that it's consistent across the 2 so that they're easily combinable. Okay. Okay. So I'm going to talk about the learning objectives for today real quick, and then we'll jump to the looking at the midterm together. So we are going to talk about map DFR today. And basically, I'd like you to understand when and how it can be used. We'll also talk about a package called FS, which stands for file systems. Okay, this is sort of a, I would describe it as sort of like a nice to have package. It doesn't do anything that's too wildly different than what you can do with the equivalent base functions. So I'll show you the base functions too, but it has some nice sort of defaults. And so I tend to use it when I'm doing interactive stuff anyway. Then we'll talk about batch loading data of a specific type within a mixed type directory. So what I mean by that is you have a directory, like a folder, right? And it has, say, 20 files, and 15 of them are CSVs and 5 of them are Excel files. And you want to read in all the CSVs, but not the Excel files, right? Or you want to read in a different directory, all the SPSS files, but not the Excel files and not the CSVs or whatever. Okay, so we'll talk about that. And then the last part is very regularly, as we'll look at today, there's actually like metadata or actual just like data associated with a file that's in the file name, right? So for example, in what we'll look at today, like the grade, the content area, and I think the testing year are all embedded in the actual name of the file, right? So the name of the file would be like G8 ELA 18 or whatever, .csv, right? And that means it's grade 8 English language arts in the 17-18 school year, okay? So what we'll talk about is how you can read in all of those CSVs and then use those file names to actually pull more data and actually add it to your data set, okay? When we're talking about list columns, we'll contrast list columns with base split, what we've been using so far. And then by the end, hopefully you should be able to feel pretty good about nesting and unnesting data frames and understand tidyr nest and unnest, which I kind of just showed a little bit, and why that's a really powerful framework. Okay. All right. Midterm. Let's look at the take-home portion together. So it looks like this. I have said here, I have some options here for showing you how to set up caching, because some of the code chunks that you'll be running here will take a fair amount of time to run. And so if you are running them every time, it's going to be pretty annoying. And so you don't have to do this, but I would recommend it. However, I also have this picture here showing you how to clear your knitter cache, because caching is kind of a complex subject and I don't really want to get into it. But what can happen fairly regularly is chunks get out of date. So for example, you have a plot that's down here, right? And then you have, and it's all good. And then you do something up here where say you're changing the theme and you go to knit it, it's still going to get the cached version of this one down here. So the plot will not actually update how you expect it to. Okay. So that's a dependency issue, but we're going to avoid that altogether. And I'm just going to tell you to clear your knitter cache entirely and reknit the whole thing. So my advice, set up caching. But if you're running into anything where it looks weird and you're like, why is this not, like I made this change and it didn't update, then clear your knitter cache and then rerun the whole thing. Okay. I have some notes about your get ignore file with your cache here too. Okay. So this has two parts, part A and part B. I think that's it. There might, yeah. And then there's a small extra credit piece that's actually not. It's not as difficult as this extra credit piece was, I don't think. It's just like additional work, okay? So to start out, I have this function for you that I'm just giving you, right? And then I'm saying, okay, now I would like you to just copy this function into your directory or into your R script and run it. And then you're going to use the function. So notice I'm not asking you to write a function. I'm just asking you to use that function to download all of the data from 14-15 to 17-18 in a single function. And it should return a single data frame. Okay, so this function just takes one argument, year. Okay, and let's see. I think I say this somewhere. Yeah, it's just the last two digits. So 15 to 18 are the possible arguments. And if you say 15, it's going to represent 2014-15. If you say 17, it's going to represent 16-17 school years, right? So all that's happening here is this year argument is getting put in here, year -1, and then year, okay? And then it's going to import the data. So it's not a very complicated function, but we haven't talked about functions. So I'm not asking you to write it. I'm just asking you to use it, okay? So using one function, you should be able to, or one line of code, basically, you should be able to download all of the school year's data from 14-15 to 17-18. Okay, notice this is real data from the Oregon Department of Education. Okay, then it should look something like this. Okay, then I'm asking you to do some basic data cleaning. Here's some things that I'm asking you to do, and it should look like this when you're done. Okay, so notice I have the level and the N. Okay, so here's the grade level. The level is like their performance category. So this is the number of students in grade 3 for this school or school district. I think it's school that we're looking at, that performed in achievement level 1. Okay, and there's one that performed in level 2, etc. Okay. Then we're going to sum across those ends for each district within each year. Okay, so here's 14-15 for Adrian School District. There's 2 schools. Here's level 1, 2, 3, 4. And we have the number performing in that category who were coded in the ODE database as Hispanic Latino, and the number who were coded as white who performed in that category. Okay, so this is 14-15, and then we have 15-16 and 16-17, etc. Okay. Then we're going to look at achievement disparities between these groups. Okay, so I say if you have not already done so, you'll have to download this package that I wrote specifically for this homework called Gapper. Okay, and it's basically just a way to estimate. Well, there's more information about it. It's a way to estimate an effect size like metric between 2 groups, as if you had the full student level data. We don't actually have the student level data. We just have what's like some people refer to as like coursing data. So we have the number of data that, or number of students that scored in each performance level category, but we don't know what their actual score was. So we're going to use that to infer the difference in achievement between those 2 groups as if we had their actual test score data. Okay, I think it's actually a really cool method. I linked to the article where this is talked about here if you want to know more, or you could talk to me because I could describe it more. So then we're going to use this like this. Okay, so here I say library Gapper, and I say D1 through 4. So I'm taking just the first 4 rows. So if we look back up here again, just these first 4 rows. Okay, so this is for 1 school district for 1 year. Okay, and then I just give it the reference group and the focal group. Okay, so in this case, I am comparing the difference between these 2 groups. And then we get these values in the back in return, the AUC, the area under the curve, V, which is the effect size like metric. This is interpreted very similarly to Cohen's D, and then the standard error around that thing. Okay, so this is telling us in this case that Hispanic students who were coded as Hispanic Latino in the ODE database scored on average about 0.8 standard deviations below students who were coded as white within this school district during this school year. Okay, and so what I'm going to ask you to do, you probably can see where this is going, is to do this for all students, for all school districts, for all years. Okay, so make this same comparison for all school districts, for all school years. Okay, I am asking you to do it in 2 ways. First, by using group by nest map, and then second by using nest by then summarize. So those are both topics for today. Okay, and then so on my computer it took about 40 seconds for the analysis. It might take a bit longer for you, but who knows. Okay, so that's the first part. That's 10 points. Then for 5 points, just reproduce this figure. All this figure is doing, and when I say reproduce, I don't care about the theming at all in this case. Okay, I don't care about the colors. I don't care about anything, except I care about knowing which is which. So the x-axis in this case is the nest by summarize method for computing V, and this is the group by nest mutate map method. Okay, but basically all I'm doing here is creating a plot to confirm that using both methods, I get the exact same estimates. So the correlation here is 1.0. Okay, that's all I'm doing there. Okay, Part 3 now is 15 points, and this is fairly complex at this point, right? And some of this will be in next lecture too, not just this lecture. But first, I'm going to get you I'm giving you some code here, right? But you're going to grab the first 100 school districts. So we're not going to do it for all of them. Probably should have even limited it more to like 50 or whatever. But I'm just grabbing the first 100 school districts. And then we're going to say, okay, your model list object, so that's what you created up here, right? You're going to filter it where your district is in this dists, okay? And then you're going to reproduce this plot for each school district for each school year. There's a couple things I want to point out here, okay? Parts of this are fairly straightforward, right? In terms of we have school year on the x-axis, we have the average achievement difference in standard deviation units on the y-axis. We have this red line here that is 0. So if there is no difference between them, we would expect them to be on that 0. And what we're seeing here is for this school district, which is Bandon School District, there was a big difference in 2014-15. It started to go down, and we actually had an opposite difference in 2016-17, and then it went back up. But both of these, like all these around here, basically it looks to me like this year was kind of an outlier. And then we've got these three, which are all pretty similar, bouncing around 0, right? So, but a couple of things to point out, right? Bandon School District. When you're doing your plots, each one of those needs to fill in which actual school district the plot is. Down here, it says, note, district included 3 schools. Some districts include many schools. Others, like Bandon in this case, only include a few schools. All right. So you need to have this vary as well. Okay. And then obviously you're going to have all of your estimates as well. Okay. And then number 4, save the plots. So that's producing the plots. And then for the last part of the actual midterm, you're going to save all the plots in the plots directory. Make sure the file names are meaningful. Okay. And that's it. This extra credit, so this is a little bit confusing. Number 4 is required, okay? There is an extra credit piece that's sort of in between these, which is, I'm not telling you which of these you need to produce, like whether you use the group by mutate map method or the nest by summarize method. You can use either one to produce these plots. But for I think 1 point extra credit, you can do another loop where you're looping through both of your model list objects and just like stapling the plots together. So you have both plots shown side by side to sort of prove that they're identical across all of them. Okay, so that's for up to 1 point extra credit. But this part 4 is still required. Okay. Questions on any of that? This is meant to be challenging. Okay, so I'm guessing that this will be challenging. It's intended to be challenging. It's not intended to be like overwhelmingly challenging. So if you are finding yourself frustrated and not able to move on with things, please do reach out to me. As always, you are absolutely encouraged to complete this as a group. Okay, so you can all complete it as a group. If you do that, I will give you feedback as a group rather than as an individual. And that would be preferable for me because then I have less grading to do too. Okay, which unfortunately this term is a very big deal for me. Any other questions? Any questions on any of that? Okay. All right. We're going to start with map DFR and then do I have a, yeah, and then we'll go to break here in just a few minutes. Okay. So I know we're already kind of deep and haven't had a break yet, but that's okay. We'll have one here in just a little bit. Okay. Map DFR. So when you're running through your iteration, when we were having like with map character, right? if the return value each time was an atomic vector of type character of length 1, then you could use map character and you get an atomic vector back in return. If when you're running through your map, the return value each time is a data frame, you can use map DFR instead, and it will row bind those data frames. Okay, so you can loop through something. If the return value is a data frame, then you can get a single data frame in return. Okay, which is very nice. So here's an example. If you would like to follow along, you can. I'll give you like 30 seconds maybe to do that. You don't have to, but it'd be good if you did. So I'll give you 30 seconds here to get set up if you'd like to follow along. Starting now. All right. Okay, so what we're doing here is I am basically creating a function that simulates some data. Okay, so this function takes an argument n, which is the number of cases we want to draw, and then it has default values for the mean and the standard deviation, but we can actually change those if we want to. What it's going to do is it's going to return a tibble for me that has a sample ID. Oops. It has a sample ID, which is just going to be a sequence, the length of n. Okay. And then it's going to give me my sample back, which is a poll from a random normal distribution, then with the n that is supplied and the mean and the standard deviation that is supplied. Okay. I'm calling this function simulate. So now when I say simulate 10, I get a data frame back that looks like this. Okay. Here's my sample ID 1 to 10, and here's my values. Okay. Cool. 2 more quick examples. Now I can say simulate, give me 3 draws from a random normal distribution that has a mean of 100 and a standard deviation of 10. And there we go, 1, 2, 3, and there's my sample. Okay. Give me 5 draws from a distribution with a mean of -10, standard deviation of 1.5, 1 through 5. There we go, all negative, right around 10. So assume we want to use this function and vary the sample size from 10 to 150 by increments of 5. This is very similar to what we've done in the past. Yep.
Can I just clarify something really quick?
Yep.
In the way you define your function as n equals 0 and are those kind of like the default?
That's exactly right. Yep. So we'll talk about this more when we get to writing functions, but this has one required argument, which is n. Okay. The mean and the standard deviation are not required. So notice when I just say simulate 10 down here, it's simulating from a distribution that has a mean of 0 and a standard deviation of 1. But on these other lines, I've actually passed what I want the mean and the standard deviation to be. And so then it's pulling from those instead. Good clarification. Okay, so we're going to use this to vary the sample size from 10 to 150. And we're going to make the mean stay constant at 100 and the standard deviation stay constant at 10. Okay. What I'd like you to do now is actually try to do this with per map. Okay, so I told you before that you didn't have to follow along. I forgot that I actually had planned out time for you to do this. So please do this. Okay, 2 minutes. Okay, with per map, this is the way I would do it. Load the tidyverse, and then I'll say map. I'm going to loop through a sequence from 10 to 150 in increments of 5. I'm going to apply the function simulate, where the mean is equal to 100 and the standard deviation is equal to 10. We could, if we wanted to, use the tilde.x syntax also instead. Okay, that's going to return a list for me of the same length that this sequence is. Okay, and so we can look at the first one, here, and we see this is the first list, right? And it's of length 10. Here's the second one. This is a list, and it's of length 15. Okay, so that's cool. But now do the same exact thing, but just swap instead of map, add map underscore DFR. Okay, 1 minute. Okay, what you should see is something that looks like this. Okay, map DFR, everything else is the same. All I did is add this underscore DFR to it, right? And what I get back instead of a list is a data frame. And that's great, right? Because data frames are easy to work with. However, we do have a problem here. If we look at our first 15 rows, we can see that sample ID goes 1 to 10, and then it goes 1 to 5, and it would go 1 to 15. So we have repeated sample IDs here, right? So we can't really actually distinguish this one from this one. We don't know which sort of poll it came from. Did it come from the one with 10 or the one with 15, right? So what we can do is we can add this .id argument, okay, which is a super, super helpful argument. I use map DFR probably 90% of the time with this .id argument, okay? What it does is each time it goes through an iteration, it's just going to add an index. So this is the first time. So basically I'm saying .id, I'm calling it iteration, but you can call it whatever you want. Okay, whatever you name .id here, that's just going to be the name of the column here. Okay, so it could be anything. It could be file, it could be whatever. Okay, and it's going to poll. Well, so there's actually two different ways it'll work. But in this case, it's just giving an index. So this is the first time it goes through. This is the second time it goes through. Okay, so now using both of these together, we can clearly identify that this is the first sample from the second iteration, and this is the first sample from the first iteration. Okay. All right, so .id is either a string or null. If it's a string, then the output will contain a variable with that name. What is stored in it is one of two things. Okay, it's either an index like we just saw, or if the vector you're looping through is named, it will include the names instead of an index. That probably isn't super clear right now, but I'll show you it right here. Okay, so here's sample size. These are the sample sizes we loop through, 10 to 150 in increments of 5. Here they all are. Okay, I'm going to say set names for this sample size thing, and I'm changing those all to English. Okay, so this is the first element of this atomic vector, and it has a name of 10. Okay, this is the, I don't know what number it is, but it's 70, and it has a name of 70. Okay, so now the vector I'm looping through, which is this one, right, actually has names. So when I use that .id argument, it provides the name there now instead of an index. So instead of saying 1, 2, 3, 4, or whatever, it's saying 10, 15, 20, 25, 30, etc. Okay, this turns out to be super, super useful in all sorts of different cases. Okay, one more quick example. There's a package called Broom that you may or may not be familiar with, which will basically take model output and put it in a tidy data frame. Okay, so here I am applying the model TV hours modeled by age for GSS cat, and I Broom tidy it, and we get the term and then the estimates and some other stuff. All right, what we can do is split this by year and then use map DFR to fit a model to each year and then Broom tidy it. Okay, and we get this data frame that looks like this. However, this is really not very helpful because I have intercept age, intercept age, intercept age, and I don't know which one is linking to which year at all, right? So what I can do instead is add a .id argument, call it year, and now I get a column that specifies the year for each of those. Why does it specify the year there? Because split up here splits by the thing, right? And that's a list, but then each element of the list is named according to the thing that you split by. So in this case, 2000, 2002, 2004, etc. So when you use split, that list vector has names, and so that's what ends up in there by that .id argument, okay? So again, super helpful in this case, because without it, it's almost impossible to make sense of. And with it, we have a beautiful data frame we can do all sorts of stuff with. Okay? Questions before we go to break? Okay, we're going to break for 5 minutes, and then we'll come back and we'll get as much done as we can in the next like 50 minutes before we do our quiz. Okay? All right, go ahead. Okay, here we go. All right. Ideally, I would like you to please follow along again. We will now shift our focus a little bit to talking about batch loading data. So this is most useful when you have data that has been separated by some sort of category. Okay. So if you look, assuming that you have the course repo cloned, you should have the data directory, right? Inside of the data directory, you will see another folder called pfiles sim. Okay, these are simulated person files from an analysis for the state that we have to do every year for statewide testing. Okay, so if we want to look at those files, one way to do it is through the fs package. Okay, so if you don't already have it installed, please do install the fs package. You might already have it installed from installing the tidyverse. I'm not sure if that's a default install now or not. It used to not be, but it could be now. But then we're just going to say library fs, and then you use this function dir_ls. This means directory list, basically, right? So what this function is going to take as an argument is a path to a folder on your computer. Okay, so I'm saying here data, what's in that data folder, and it's going to tell me everything that's in that data folder. Okay, if I say here data pfiles sim, it's going to give me a whole bunch more files, right? Those are the files that we're actually going to be reading in. So again, please do follow along if you can. We're going to work together to batch load these files in, and then we're going to work with that path to actually parse data from the file name. Okay? So while you're doing that, I'm going to just continue to talk so we can get through more, because that part's not terrifically important. Limiting files. So very, very regularly, most of the time, I would say, you have data that are in multiple formats. Okay, so if you have data that's really well organized, maybe you have a folder that's just CSVs for just a specific thing, and that's great. But even so, somebody else could go and add something to that folder at some point, especially if you're working with shared drives, right? So what you can do instead is give it what's called a glob, okay, which is basically just the extension on the file. And so here, in this case, I only want the CSV files. So I'm going to say here data pfiles, and then I'm going to say the glob is star, meaning anything. It can be anything, but then it's going to end with .csv, okay? And that gives me back just the CSVs. In this case, actually, that is all that is in that folder, okay? But even so, this is going to be a little bit more safe, because somebody else, including you, might forget and add an Excel file to that directory. And then later down the line in your sort of data pipeline, you might try to read in all the data from that folder, and it might throw an error because you're trying to read it in an Excel file with read CSV or whatever. Okay. So now, though, now that we have this, we want to be able to basically loop through all those file paths and read in the data, right? So what we can do is first list all those files. So in this case, I'm actually saving it in something called files. And then I'm going to say batch or whatever, you can call it D, you can call it whatever you want to call it, right? I can say map DFR files read underscore CSV. Okay, so I'm going to loop through all those files. I'm going to read underscore CSV to them. I'm using batch or map DFR because each time I apply read underscore CSV, it's going to give me back a data frame. So using map DFR, it binds all of them together. And in one line of code here, I've read in however many files that is, many files in a single line of code, and I have a single data frame in return that's about 16,000 rows. Okay. Go ahead and try that if you haven't. Does anybody see a problem with this though?
We set no ID, so there's no way to discern which data comes from which one.
That's exactly right. We didn't use the ID, and so we don't know where the data came from in each of these. So we already said this, but so we're not going to actually do this, but we need to fix it, right? We need to fix it, and we can fix it by specifying an ID. So now we can do this same thing, but we can pass this additional argument .id, and in this case, I'm calling it file, okay? Because that's what it is. It's the file that I read it in from. If I try to actually look at it, it prints like this, which is not very helpful for me, at least on my slides. If you do it on your computer and you pulled your screen out really, really wide, then you might be able to actually see something. But the reason why is because this first column, file, is so long that it can't fit on the screen. So it's just showing me no rows. Okay. Even if I say count file, so it's just showing me the file, it doesn't show me anything. Okay. So what I can do to make things a little more manageable is I can first remove the here part. Okay. Because when I do here, right, if we go back to these files, we're getting the entire path, right? The whole thing from the root of my computer, basically, all the way through to that file. I don't really want that in this case. I don't want all of that stuff. I just want to know what the file name is. Okay, so that was important for importing, but it's not important for actually pulling data from there. Okay, so I have my batch 2, which is what I use the .id file on. And then I'm going to say mutate file. I talked about this last term, but I actually typically use gsub. But in this case, I use string replace all. So which is the equivalent, right? It's the tidyverse version. But I'm going to basically go through file, and I'm going to say here data p file sim. So find that pattern and replace it with nothing. Okay. And now if I say count file, I get something that looks like this, right? So you can see the first file was grade 11, English language arts, p files for 17-18. Okay. Questions? Does that make sense? Okay. Now, what's really neat about this is I actually have in here, as I kind of talked about earlier, I have a bunch of data in this file name, which I do not have represented in the actual data itself. Okay. I don't have the grade or the content area. I might have some of that, but I don't have all of it. Okay. So what I want to do now is use that file name to parse that data. So this is where regular expressions are going to be super, super helpful. And we talked about them a tiny bit last term. We didn't go into a lot of depth with them. As I mentioned last term, I would say 90% of your work, if not more, can be accomplished without regular expressions. But at a certain point, you get to the point where it's like, okay, I'm writing these 5 lines on the same thing over and over again to try to get one thing. it'd be neat if I could just do a single regular expression to take care of all of that, right? And so we're going to do the regular expression approach here. I'm going to walk you through what I'm doing. It's a process called back referencing. Okay. This is, of course, not the only way to do it, but hopefully you will understand the logic of what I'm doing in this specific case, and then it'll help you kind of think more generally about this. Even if the exact approach that you take to get this is not the regular expression approach, that's fine. Okay. So first, let's say I wanted to pull grade. Okay, so the grade is right here, G11 ELAP files. But this is a little bit tricky because in this case, it's grade 11, so there's 2 digits, right? But in every other case, it's only 1 digit. So if I said pull the grade and I said just give me the second character, whatever that is, well then for grade 11, I would get a 1. And actually then I could take care of that in a second step because there is no grade 1 in these data. It's grade 3 through 8 and then 11. So I could say just give me the second digit and then go through that and say if it's 1, change it to 11, right? That would be a totally reasonable way to do it. Instead, though, I'm using a regular expression. So what I'm doing is I'm saying it is, and I probably should have even put a caret here to say starts with. So it has the /G, and then notice I have parentheses here. The parentheses are what I want to pull out, okay? And I pull that out through this /1 on the second as the second argument. The reason it's 1 is because you can have multiple things that you're going to pull out of a string. So this is the first one. If I added additional pairs of parentheses, then I would refer to them in different orders. So I could say //2, //1, //3, right? To refer to the second one and then the first one and then the third one. In this case, there's only 1, so it's only going to be //1. But what I'm doing here is I'm saying, okay, so there's a slash, then a G, and then pull out some stuff after that, right? That's what this is, pull out some stuff. What I'm going to pull out is a digit. That's what that //D means, a digit, and then question mark, maybe a second digit. And this actually goes in the opposite order. So this is saying maybe this one, but definitely at least 1. Okay, so maybe 1 digit, but or definitely 1 digit, but maybe 2 digits. That's what that's saying. Okay. And then after that, there's going to be any character, any number of times. So there's going to be a bunch of stuff after that. Basically, just ignore that and just give me what's inside of there. Okay. And so then I'm just selecting file and grade here, and you can see here's my file and here's my grade. So we get 11s. What I would actually probably do at this point is count that and make sure that I'm getting 3, 4, 5, 6, 7, 8, and 11. Okay. And we actually will do that at the end, but I would actually probably normally do this in process as I'm writing it. Okay. Another way we can do this that's much simpler is just by using parse number, which is from readr. Parse number is one of the most underrated functions in the tidyverse, I think. It's a really nice function. The problem is it works great in this case, but the way it works is it's always going to pull the first number. Okay. And so in this case, it's 11. But if we were trying to pull the year, for example, which is 18, it wouldn't work. Right? We couldn't use parse number to pull the year. There are workarounds, which I've done in the past, which is like limit this to only like this part of it. So just like drop the first 5 characters or something like that, and then parse number from that. But again, the regular expression is probably going to be better. All right. Next, we want to extract the year. So this is how we're doing it. I'm just looking at the pattern. I'm saying there's going to be some character any number of times, and then there's going to be the word files. Okay. Why is that? Because that's what's down here. Okay. Then I'm going to pull out some stuff. In this case, I know it's always going to be 2 digits, so I don't have the question mark. Okay. So parentheses, digit, and then a digit, and then it's going to be _sim, and then some other stuff. Right. And I'm saying just give me the first one of that back, and we get 18 there. For content area, this one seems like it could be a little more tricky, but if you're using regular expressions, it's really just the exact same process, okay? Because we have the grade, and then we have the content area, and then it says P files. The content area, though, is ELA, math, science. I think we even have reading and writing, okay? So the length of that is going to really depend on the content area. So we can't deal with it by length. So we're going to say it starts with a G, and then there's going to be a digit, maybe a second digit, and then there's going to be some stuff, and that's what we're going to pull out. Okay. And then it's going to say P files, and there's going to be some more stuff, right? So we want after the digit and maybe the second digit, we want everything in there until we get to P files. Pull that, and in this case, we get ELA. And then we do our double checks, right? So here I say count grade. Notice we get 3 through 8 and 11. That's great. Count year. In this case, it is only 1 year, so we probably didn't have to do all that work, but we did it anyway. But that's great. For the content area, that all works too. Notice these are all different lengths. It's fine, right? And so then we just finalize it where we have our batch 2. We're going to mutate. So we're going to compute grade, and then I'm changing it to an integer because up here it is still a character. Year, and then changing that to an integer, and then content area. And then I'm selecting, and notice now I'm saying, okay, now we can drop file. I've used that column as much as I want to. I can go ahead and just drop that file. I've got all the data I need from it. And now every row is going to be identifiable, right, in terms of where it came from. And then I'm just going to select some columns in the order that I want them to be. Okay. And this is the final product. So this, in this case, we basically have a tidy data frame already. We don't have to do anything else. We're done. Okay. But you can see, you know, some of this stuff we pulled from the name of the file, which is, in my experience anyway, is a very common way that often important data is stored. And so had these data been stored slightly differently, so they had all of those columns in there already, we could just do map_DFR and just omit the .id argument and we'd be fine, right? But in this case, it did not have those. And so we have to use that map_DFR to be able to identify which rows represent which data. Okay, so we've reduced our problem from 31 files to now a single file. Okay, in my mind anyway, this is like a super powerful approach. And when I first learned of it, I was super excited. So once we do this, we can do all sorts of different stuff, right? We can do a quick look at all the distributions. We can look at summary stats, so I can group by grade, content area, and primary disability code, and then summarize to get the mean theta, which is their score, and then end up with something like this. So this is like a table for a report, right? Okay, backing up a little bit though. Let's say we wanted only math files, okay? If we want only math files, we can't use that glob, okay? Because the glob is just for the extension. So what we use instead is Regex, okay? Which stands for regular expression. And so then within the Regex argument, you just pass it a pattern that you want it to search for. And you can pass it an actual full-on regular expression, or you can just say, here's the pattern I want you to look for, and it will only return the files that match that regular expression, that match that pattern. Okay, so in this case, I don't actually have to do an actual regular expression. I can just say math, and it returns just the math ones. Okay, so what I'd like you to try now for the next 3 minutes is to try to read in only the grade 5 data. Okay, I'm not going to ask you to do all the parsing of everything like we just did. That was more sort of showing you an example of how you might do this, but I'm not going to ask you to actually do it. But I would like you to try to read in only the grade 5 data and try to read in all of the grade 5 data. Okay, 3 minutes, go ahead. Okay. Hopefully you were successful. Basically, it would look like this. We get the grade 5 tags like this, DIRLS. We're going to say here, data, p-file sim, and then the regex is just G5. Okay. From there, we just say map_DFR G5 paths, read CSV.id equals file. Okay. And then I replace the here part on there so that we end up like this. Okay. And we have ELA. We would also have math. We would also have science, etc. Any questions on that? Okay. I'm going to mention for just a second the base equivalents for FS. The one that you may have seen before is called list.files. I use list.files a lot. There's nothing that's wrong with it at all. If I call list.files on p files, sim, data p file sim, I get something that looks like this. Okay, so notice even though I'm in a nested directory, all I get back is the actual file name. And so I can get the full path back by adding an additional argument, full.names equals true. Okay, and that's pretty nice. Or only CSVs by adding this dot pattern or this pattern argument, where in this case I just pass the same sort of syntax that I do with dirls. Okay, so why not use base? What's the advantage of using FS over list.files? They're not huge, but there's a few advantages. The first is, as I showed you just a second ago, what it returns by default is just the file name. And so if you're working in a nested directory, like I often am anyway, then you have to remember to say full.names equals true, or else you'll end up with this. It can't find the file that you're trying to read in because it doesn't live there, right? Because what you're looping through here in files is just the file names. It's not actually the file paths. Okay, so that can be confusing and hard sometimes. So here's just an example. This is what we're looping through. None of those files live in that current directory, so we fail. Okay, so we have to return the full names. So we can say full.names equals true, and then we can say mapdfr, and now I add this .id equals file argument, and I get something that's far less helpful. I just get an index 1, 2, 3, 4, etc. Why is that? Well, because list.files by default just returns the file names, etc. But it also doesn't have names. FS by default has the path, and the name of the element is the path. And so when per is looping through it, it gives you that path back here instead of giving you back an index that is much less helpful. Okay, so if I say names of files, we get null. So in this case, right, this index is not super helpful. It's helpful in terms of differentiating the data, but we actually need to pull data from that. So what would probably be the most helpful is to do something where we're first getting the full names, and then this is just exactly replicating what FS does, where I'm saying set names of files is files, okay, and then everything is the same. But what would actually probably be the best is if we said list.files without full names equals true, and then list.files again with full names equals true. Then we could loop through, then we could set the names of the file paths to be just the file names, okay? And then that would probably be the best of both worlds, but that is not what we do. So we could write our own function with that uses list.files to do that if we wanted to, but that's not what. Okay, so my general recommendations on this, if you're working interactively, I find FS to be more useful and more helpful, and there's no reason not to use it. If you're building functions that take paths, you could use FS, or you could use the base list.files, right? Either one is an option. So in that case, it might be worth skipping the dependency and just using base list.files. However, every time I have this sort of a conversation, I have to sort of preface it with dependency, like thinking about dependencies is like complicated, right? There are people that will say you should do everything you can to avoid all dependencies. I think that is not smart, okay? Because especially if you're dealing with dependencies that are from packages that are put out by the RStudio group, those are professional programmers that are programming every day and have a whole bunch of tests to make sure that their packages work well. Okay, so depending on them is can still lead to headaches for sure, but you can be pretty sure that those packages are going to work in the future. Okay, so if it really helps the functionality of your package to depend on something, especially from a professional developer group, then I would say absolutely do that. The problem with dependencies is that they can become outdated, which then ends up with bigger maintenance problems for you down the line. But also you can end up with your package being like bloated. So it's a way bigger package than it needs to be because you're depending on all these other things. So instead, I generally try to keep my dependencies as low as possible within reason. So for example, if I have to import JSON data in my package, I'm not going to write my own JSON parser, right? That's silly. I'm going to use a package that already imports JSON data, and I'm going to use that. But for other things like this, I'm going to use list.files instead of FS because there's really not that big of a deal between them. Okay, so that's just my approach, but whatever you want to do is fine. Okay, we have about 20 more minutes, so we'll at least introduce list columns. We'll get as far as we can, and then we'll have our quiz. Okay? Any questions before we move on, though? Okay. All right. Let's say we want to compare models. So let's say we're using this data that we have now that we just read in, and we want to fit 3 different types of models. The first includes, so theta is the outcome. Theta is like the student's score on an IRT metric. Okay, this thing is the student's primary disability code. Every student in this data set should have a disability code. Okay, so this is their primary code. And then this one is their secondary disability code. So they have a primary code, and then some students have a secondary code, not all of them. Okay, so this is basically adding secondary disability as an additional predictor of their score. And then this one is looking at the interaction between their primary and their secondary disability to see if that predicts their score. So we might want to know if like how these models fit. Does this model, including their secondary disability, contribute to the model above what just their primary does? And after that, does modeling the interaction between them make sense? Or does that actually not add anything new to the model? Okay, so that's what we're going to do. And in this case, because of how the data are, these are statewide data, we're going to probably need to split them to get this done. Okay, so couple of things, just sort of house cleaning before we really get started. The disability variables are stored as numbers currently, okay, and we need them as factors. So yeah, so we're going to just change them to this like this. So we'll just say as.factor on each of these things, and we're making the names easier, so it's just primary and secondary instead of these things. Okay, if you're interested in what these codes actually mean, I have a link here to the statewide documentation. Doesn't really matter too much for our actual purpose of illustrating the code, but just in case you're interested. Okay, so we've been doing this like this, right? We're going to fit separate models for each content area because it doesn't make much sense to fit a model across content areas, right? So especially because students have 1 score per content area mostly, although not in all grades, but we'll talk about that more in a second. Okay, so I first could split the data by content area, and it looks like this. Okay, then we could go about fitting our models like this, where I'm saying map through split content and apply this model, map through split content and apply this model, map through split content and apply this model, right? And we get M1, M2, M3. Then we could do our tests to see which fit better, et cetera, okay? Alternatively, we could use a list column with our data frame, okay? So in this case, I'm taking my full D object and I'm saying group by content and then nest, Okay, so what this is doing is we're going to get one row per content area. Okay, so whatever you group by, you will get one row per thing that you group by. So you can group by multiple things and you'll get one row per combination of those things that you're grouping by. All right, and then you're going to nest and you end up with a list column for the data. Okay, so what this is this is our identifier for the grouping, and this is all of the data for ELA in one cell of the data frame. Okay, and this is all of the data for math in one cell of the data frame. Okay, yes. So this cell of the data frame has an entire data frame within it. So that's why this is a list column. It's like a column of the data frame, but it's actually a list where it has each element of the list is a data frame. Okay. So if we look at by content data, right, we're pulling the data column, we can see it looks an awful lot like the split object that we had before. Okay, the only difference is it no longer has this content column in it. Okay, this content column gets pulled out of the data, and that's not in here, but everything else is. Okay, so it's just like base split. So we can explore it a bit, right? We can loop through our data with map double and compute the number of rows. And you can see they're mostly similar, but they're not the exact same. And this one in particular is much smaller, right? That's probably because that's science and that's only in 3 grades as opposed to all grades. Okay. We can also look through the columns and we get the same number. And we can do things like compute the mean of theta for each of them like this. But even better, it's a data frame, right? So we can actually add columns to the data frame that summarize that data. Okay, so I can say how many rows are in each of these data frames, and I just pass it through mutate like I would normally. Okay, so by content mutate n is going to be equal to map double. So I'm going to loop through this data list column, and I'm going to compute the n row, the number of rows. And notice because I did map double, I get just the numbers here as a new atomic vector in my data frame. So that's basically what I just said there. What do you think would happen if instead of using map double, I just used map? What do you think would happen? It would work, but yep. It would be a list column. That's exactly right. We would get a list column back because map always returns a list. Okay, so it would look like this. Notice each of these is of length 1. And so that should be a clue to us immediately that we should have used map int or map double, right? But, and in this case int, but we used double, but whatever, it's fine, right? So this is not nearly as helpful. It's much better to use map double where we can actually see the values here. Okay. Questions? This is, in my mind, a super powerful framework, and it takes some time to wrap your head around like an entire data set is in a cell of my data frame. But once you do, it will be really helpful. Okay. So now we can continue with this where we can fit a model. All right. So I'm going to start out with just my first model. I'm calling it M1. Okay. And I'm doing this inside a mutate. So now I have a new list column that is all of my M1 models. Okay. One for each content area. I can do it again where I'm pulling, now I'm looping through M1 and I'm pulling the coefficients. And notice I'm using map because these are length 11, 12, 11, 12, 12, right? So these are, unless they're all of length 1, I can't use map double or map whatever, okay? I'm going to skip over this because we only have like 10 more minutes until we're going to do our quiz. So I'll just show you. Let's say we wanted to continue with it, but we wanted to end up with something that had 3 columns: the content area, the intercept, and then a value for TBI, which is traumatic brain injury, okay, which is code 74. So we want to know basically what's the average score for the reference group, whatever that is. And then, which I can't remember, but we'll probably, no disability is the reference group. And then what the score is for average score for TBI. So what I can do here is I have M1 and COEF, right? This is all the same as I did before. But then I'm creating another column, which I'm calling no disab. Okay, and I'm just going to map double. I'm going to loop through my COEFs up here. And I'm going to say, give me the first one. That's the intercept, right? That's just like in the lab that we did last time. And then for TBI, I'm going to actually take that no disab and I'm going to add to it the coefficient for primary 74. During the challenge, I was not actually expecting you to add these together. So just this part that I have highlighted is what I was expecting. But this will actually give you the mean for TBI. So now we can see the mean for no disability and the mean for TBI across all the content areas. Okay. Back to our original task. And again, I'm just going to illustrate this stuff so we can get through as much as we can in the time that we have left. We want to compare these different models. Okay, so first we need to actually fit all of these models. So what we can do is use a mutate, and then we can just say M1, M2, M3. We can map through data 3 different times and apply our 3 different models where we're using .x, right? So these map calls are all exactly the same as we've done before. They're just happening inside of a mutate call. Okay, and then we're looping through we're looping through this data list column. Always in this case. But as we saw before, I was looping through the data, and then I was looping through the models, and then I was looping through the coefficients, right? So you can loop through any column that you want. And then next week, we're going to talk about parallel iterations, but I just want to show you real quick. If we wanted to compare these 2 models, so this is from the first row, right, which would be ELA. Here's the model 1 and here's model 2 for the first row. The way we would do this is with ANOVA. Okay, so we would say ANOVA mods M1, mods M2. Okay, and we get this comparison in return. What we can do is we can use map2, which is the same as map, but iterates over 2 vectors instead of 1. Okay, so if we wanted to compare models 1 and 2, what we could do is we could take all those models and we could mutate, and I'm creating a new thing I'm calling comp1-2, so comparison between model 1 and model 2. And I'm saying map2 map through M1 and map through M2 and apply the function ANOVA. Okay, and then we get all of the ANOVA comparisons for the difference between model 1 and model 2. Okay, this is still not terrifically helpful because we still have all of these list objects. We could then print all the list objects and get what we want if we needed to. Or better, we could programmatically pull things from there that we want, right? So one of the things we might want, although it's one of my least favorite things, but is the p-value, right? We might want to know what the p-value is in that comparison. So what we could do is go back to our original thing, right? I did it for 2 models. I called it compare when I was looking at just for ELA, the first one. So what I would do is I'd go back to that one and I would try to actually pull the p-value for that one singular case. And I did it like this. These are 2 different methods to do the same thing. But this actually still doesn't get me what I want. It's close, but it doesn't quite, because it gives me a vector of length 2 in return, where the first element is NA. Okay, so what I really need to do is grab the second element of that vector. That gives me just the p-value. Okay, so this is what I do. And so how I would do this one of the ways I could do this is map double through my comp1, 2 and do this list, pull that thing, and then give me the second one. This is that really compact syntax I showed you before that is like at the start that is kind of confusing, and I wouldn't necessarily expect you to remember it. So a different way to do it that I think would be much more preferable is to just write a function to extract the p-value from any ANOVA object. Okay, so here I'm calling this ANOVA ob. It could be any ANOVA object, right? And then I just fill that in here. All the rest of this is exactly what I had before. And now we can just loop through comp1, 2 and say extract p. Okay, and then we get all of our p-values. Notice I'm using map double here, so we get the actual p-values. Okay, we have 5 minutes left. I'm going to skip over this part. I just want to show you. We'll get to this next time. Okay, so this is basically where we will start next time. That part I skipped over, you can look at if you want. It's an alternative way to write functions called compose through per. But I really want to show you just this last part. So we fit all the models here, right? But then what's nice is we can because it's just a normal data frame, we can do data frame sort of stuff, right? So this is what the data frame looked like before. I have all these different list columns, one for the data, one for model 1, one for model 2, and one for model 3, all of these different list columns, right? But I can pivot longer and say M1 to M3, the names are model and the values are output. So now I still have the data. I could actually probably drop that data column if I wanted to, but I have model 1, model 2, model 3, and then I have the actual model like this. Okay, so it's more of a longer format. And that's super nice because then I can do things like, okay, I'm going to extract the R squared out of all of the models at once, right? After I've pivoted longer, I can extract the R squared from all of them at once. And then I can do things like this where I can actually produce plots of all the R squares. Okay. We looked at unnest a little bit. I'm going to pause there. So I will go back through this next time. I will make sure that we talk about the other way. So we looked at today, we looked at group by, nest, mutate, map, right? That's what we looked at today. Or next week, we will look at row-wise summarize. Okay.